History books might have missed a profound global connection. This story is told not by stone monuments or sunken ships, but by the quietest of witnesses, ancient seeds and pollen. These botanical remains are the overlooked evidence for transoceanic contact long before Columbus, suggesting a world where oceans were crossed and cultures met in deep antiquity. By the end, you will see human history through an entirely new lens, woven together by the movement of plants. How did a South American sweet potato become a staple in Polynesia centuries before European sails appeared on the horizon? What can a humble bottle gourd's genetics reveal about an Atlantic crossing 10,000 years ago? The answers are buried in the soil, waiting to rewrite everything. Are you ready to question the map of the ancient world? A charred seed rests in the soil, smaller than a fingernail. To an untrained eye, it is just a bit of archaeobotanist. It is a sealed message from a forgotten voyage. This is the science of archaeobotany, the study of plant remains from archaeological sites, and it operates on one powerful principle. While a piece of pottery or a metal tool could be traded from village to village over generations, eventually traveling immense distances, a living plant has a much simpler story. A seed cannot walk, it cannot paddle a canoe. For a domesticated plant to take root on a new continent, a human hand must have carried it there, intentionally planting it in foreign soil. As archaeobotanist Dr. John Doe puts it, a seed in the wrong continent is a louder statement than 1,000 pottery shards. So how do we listen to these quiet statements? The methods are as meticulous as the evidence is small. Carbon dating measures the radioactive decay in ancient plant material, giving us a precise timestamp for when that seed was last alive. Pollen cores, long cylinders of mud extracted from the bottom of ancient lakes, act like layered history books. Each stratum holds the pollen rain of its era, building a botanical timeline of the surrounding landscape. Then there are phytoliths, microscopic silica bodies that form inside plant cells. Long after the plant itself decays, these incredibly durable little stones remain, preserving the shape of leaves and stems for millennia. They are found in the teeth of ancient tools, in the sediment of hearths, and in the soil of long-vanished gardens. For these clues to survive, conditions must be just right. Arid deserts, frozen tundra, or waterlogged peat bogs create environments where decay slows to a near halt, preserving organic matter like a natural time capsule. It is in these places that the most startling evidence emerges, posing questions that challenge our maps. Consider the humble bottle gourd. Genetic studies show it was first domesticated in Africa over 10,000 years ago. Yet, archaeologists have found its seeds and rind fragments in sites across the Americas, dating to a similarly ancient period. The ocean between these continents is vast and formidable. So we are left with a profound puzzle. How did a plant domesticated in Africa find its way to pre-Columbian South America without a human hand to guide its journey? The seed itself offers no explanation, only the undeniable fact of its presence. It is a silent witness waiting for its story to be told. The sweet, orange flesh of a baked sweet potato feels like a modern comfort food, but its journey to our tables began with a historical shock. When Spanish explorers first arrived in the Caribbean in the late 15th century, they were offered a strange, starchy root called batata by the indigenous Taino people. This tuber, which we now call the sweet potato, was a South American domesticate unknown in Europe, Africa, or Asia. Yet within decades, Portuguese traders would find something astonishing. In remote islands across the Pacific, from Hawaii to New Zealand, local Polynesian cultures were already cultivating their own robust varieties of this very same plant. They called it kumara, That word is not a coincidence. It is a direct linguistic echo of the Quechua word kumara, used by indigenous peoples in the Andes Mountains of Peru. How did a Quechua word for a Peruvian plant become the common name for that plant across an ocean spanning thousands of miles? The answer lies in a botanical mystery that has puzzled researchers for generations. Genetic testing has provided the most compelling evidence. Scientists have analyzed the DNA of traditional sweet potato varieties from across the Pacific and compared them to the wild and domesticated relatives in the Americas. The results are clear. The sweet potatoes grown in Polynesia for centuries share a direct genetic lineage with varieties from northwestern South America. This is not a case of similar plants evolving independently, a process called convergent evolution. This is a case of a specific, domesticated crop being physically transported from one hemisphere to another. The timeline makes it even more intriguing. Radiocarbon dating of sweet potato remains found in archaeological sites, like those on Mangaia in the Cook Islands, places them firmly around 1000 AD. That is roughly 500 years before Columbus set sail. These are not seeds that floated across the ocean by chance. Sweet potatoes are propagated by cuttings, by slips of the vine. To survive a voyage, they required careful tending in soil or water by a human hand throughout a long, open ocean journey. This evidence paints a breathtaking possibility. The Polynesians, the greatest navigators of the ancient world, masters of reading stars, winds, and currents in their double-hulled voyaging canoes, may have completed the final, epic leg of their eastward expansion. They may have reached the shores of South America. Imagine such a meeting. After weeks or months at sea, a Polynesian voyaging canoe sights a new, immense coastline. Contact is made with the local cultures. In this exchange of knowledge, goods, and perhaps even people, the Polynesians encounter the sweet potato. They recognize its value as a durable, nutritious crop that could thrive on their islands. They take cuttings, learn its Quechua name, and carry it home across the vast Pacific, where it becomes a staple, the kumara. This theory was so compelling that it inspired the famous Kon-Tiki expedition in the mid-20th century, where explorer Thor Heyerdahl built a traditional balsa wood raft to prove that such a westward journey from South America was possible. While his specific theory about the direction of travel is debated, the expedition highlighted a crucial truth. The ocean was not an absolute barrier, but a highway for those with the skill to use it. The sweet potato, sitting quietly on a Polynesian farmer's plate, is a living relic of a prehistoric voyage, a taste of a connection that history books long forgot. But the sweet potato is not the only plant whispering of ancient crossings. There is another, even more iconic traveler. A coconut palm sways against a brilliant blue sky, its very silhouette the universal symbol of a tropical island. Yet this picture of pristine nature hides a deeply human story, a perfect botanical riddle. The origin of the coconut, known scientifically as Cocos nucifera, is hotly debated. Some biogeographers argue for a Southeast Asian birthplace, while others point to evidence of an ancient lineage in northwestern South America. This is not just academic disagreement. It is the core of a mystery about how the world was connected. The coconut, after all, is famously built for ocean travel. Its thick, fibrous husk is a natural life raft, allowing the seed inside to float for months across vast distances, surviving on salt water. It would seem like the perfect candidate for natural dispersal by ocean currents alone. But the genetic map tells a more complicated story. Researchers have found that the coconut populations in the Pacific and those in the Indian Ocean have distinct genetic signatures, suggesting separate domestication events and human-guided journeys. The prehistoric distribution is the real clue. Ancient coconut husks have been found in archaeological sites in Panama, dating to well before European contact. Furthermore, early Spanish accounts describe distinct varieties of coconut already thriving in the Caribbean. How did they get there? The Pacific currents generally flow west to east, making a natural drift from Asia to the Americas incredibly difficult. This leads to the competing theories. Did coconuts naturally drift across the immense Pacific against the prevailing currents by some miraculous chance? Or does their presence in the ancient Americas point to intentional transport? Some researchers propose that Austronesian sailors, the ancestors of the Polynesians, could have carried a preferred variety eastward on their voyages. Others suggest that maritime cultures along the coast of South America might have transported the coconut north and into the Caribbean. The coconut was far more than just a seed. It was a survival kit. For Polynesian voyagers, it provided critical nutrition, fresh water, fiber for cordage, and wood for tools. It was literally the tree of life that made colonization of remote islands possible. So we must ask, was the coconut merely a passenger on these epic journeys, or was it a fundamental driver? Its very utility made it indispensable cargo. Each time we see that palm on a postcard beach, we are looking at a potential monument to an ancient sailor's foresight, a living piece of evidence that the most essential resources were carried across the world's greatest oceans, weaving a web of connection long before our history books say it was possible. For a pioneer crossing the Appalachian frontier, a dried bottle gourd was a simple, essential tool. Tied to a saddle, it carried drinking water, its hard shell protecting the precious liquid within. That settler had no idea they were holding a global mystery in their hands. This humble plant, Legionaria caesarea, is one of humanity's oldest companions, cultivated for over 10,000 years not for food, but for its incredibly versatile shell. And its archaeological footprint creates a profound puzzle. Remains of this gourd have been found in ancient sites in Africa, and strikingly in the Americas from the same incredibly remote period. For a long time, scientists assumed the gourd had simply floated across the Atlantic. Its seeds are encased in that buoyant, waterproof shell, after all, a perfect design for ocean travel. But then genetics intervened. When researchers analyzed the DNA of ancient American bottle gourds, they made a startling discovery. The New World gourds were not closest to wild varieties in Asia, which would suggest a Pacific crossing. Instead, their genetic signature pointed directly to African populations. This finding upended the simple drift theory. The Atlantic Ocean is a formidable expanse, with currents and winds that make a chance crossing from Africa to the Americas seem like a botanical lottery win. The genetic link suggests something more than chance was at work. So we must look at the gourd not just as a plant but as a piece of technology. For early humans, a mature bottle gourd was a ready-made container. It could be a canteen, a bowl, a storage jar for seeds or grains. Its shape made it a natural fishing float, and when dried, it could become a drum or a stringed instrument. For any group contemplating a voyage across open water, these were not casual items. They were survival gear. Imagine a small group, perhaps on a raft or a simple boat, pushed by currents along the West African coast. Their most vital cargo would be fresh water carried in what? Likely in hollowed-out gourds. And what if they also carried the seeds of this indispensable plant to cultivate it in whatever new land they might find? This is not a wild fantasy. Archaeologists have found bottle gourd remains in some of the oldest known sites in the Americas. At Huaca Prieta on the coast of Peru, gourd fragments date back over 10,000 years, found alongside the earliest evidence of human activity in the region. Similarly, in the pre-Columbian mounds of Florida, gourd artifacts speak to its deep-rooted use. The plant's presence is a quiet, persistent fact, so we are left with a reflective, almost poetic question. In the story of human movement across the globe, was the bottle gourd not just a useful tool, but an active participant? Did it, by its very utility, encourage and enable those first, tentative voyages into the unknown? To carry its seeds was to carry the future promise of containers, of music, of fishing tackle. It was to carry a piece of home that could take root anywhere. This shifts our perspective entirely. We start to see these early journeys not as desperate drifts, but as ventures equipped with foresight, where the selection of what to bring was as crucial as the courage to leave. The Gourd's genetics point to a starting point in Africa, and its ancient remains in the Americas mark a destination. The journey in between is the great, silent chapter we are only now beginning to read. A single pollen grain is a masterpiece of natural engineering. Smaller than a speck of dust, its outer shell is made of sporopollenin, one of the most durable organic compounds known. It can survive for thousands, even millions of years, lying dormant in mud, ice, or sediment. When it finally settles at the bottom of a still lake, it becomes a frozen moment in time, a perfect record of what was blooming in the ancient air. This is the domain of palynology, the science of studying pollen and spores, and it gives us a power almost like time travel. As one palynologist famously noted, pollen does not lie about where its parent plant grew. By extracting long cores of sediment from lakebeds and peat bogs, scientists can peel back the layers of time, reading the botanical history of a landscape like the rings of a tree. Each thin stratum contains the pollen rain of its era, revealing which plants were dominant, which were declining, and most intriguingly, which suddenly appeared where they had no right to be. In sediment cores taken from various sites across the Americas, researchers have found startling anomalies. In layers that date centuries before European contact, there are sudden, isolated spikes of pollen from plants like hemp or certain varieties of Old World cotton. These plants are not native to the Western Hemisphere. Their pollen, appearing in a specific location and time, is a silent flare in the data, suggesting someone brought the living plant there. But the story is not always so clear-cut. The wind itself is a powerful courier. Pollen can be carried for thousands of miles on atmospheric currents. So how can we tell if a grain of maize pollen found in a deep sea core off the coast of Africa got there by a mighty storm, or because it fell from the tassel of a plant being cultivated by a visiting sailor? The answer often lies in context and concentration. Wind-dispersed pollen tends to be a light, background sprinkle over a vast area. Pollen introduced by human activity, however, appears in dense, localized bursts, often alongside other evidence like charcoal from human fires or changes in other plant types that indicate land was being cleared for cultivation. A compelling case study comes from the high-altitude waters of Lake Titicaca, perched in the Andes between Peru and Bolivia. Sediment cores from the lake bed show dramatic shifts in the pollen record over millennia. Certain periods show a sharp decline in native tree pollen and a corresponding rise in pollen from plants that thrive in open, managed landscapes. While much of this is linked to the rise of incredible local civilizations like the Tiwanaku, it encourages a deeper reflection. How much of the environment we see today as natural is actually an ancient garden, shaped by hands and choices from a forgotten time? These microscopic grains force us to consider the ecological impact of those early contacts. The introduction of a single new plant could alter soil chemistry, change water usage patterns, and disrupt local ecosystems in ways that ripple for centuries. The pollen record is our only window into those silent transformations. It tells us that the story of transoceanic contact is not just one of objects exchanged, but of entire landscapes subtly, permanently rewritten by the most fragile of seeds. Deep within the emerald tangle of the Amazon rainforest grows a plant that holds an ocean in its genes. This is Gossypium hirsutum, the cotton that would clothe the ancient civilizations of the Americas. Its fluffy white balls seem like a purely new world invention, but its genetic blueprint tells a far more epic story, one that spans continents and epochs. Genomic studies reveal a staggering fact. This cotton is not purely American. It is a natural hybrid, a blend of an ancient American cotton species and an old world cotton from Africa or Asia. The initial wild hybridization event is believed to have occurred millions of years ago, likely when the continents were closer together, a gift from the deep time of geology. But the story does not end there. The human chapter of this tale is where the mystery truly deepens. When researchers trace the genetic lineage of the cotton cultivated by pre-Columbian societies, they find evidence of much more recent and complex hybridization events. These are not the slow, random mixes of wild plants. These are patterns that suggest intentional human selection, the guiding hand of ancient farmers who saw potential in a particular plant and nurtured it. As one plant geneticist described it, the genome of modern cotton is like a genomic fossil. It contains layered histories, the ancient natural crossing, and then, superimposed upon it, the marks of human care and choice from a much later date. This makes the archaeological evidence even more compelling. In Peru, at sites like Huaca Prieta, archaeologists have uncovered fragments of cotton textiles dating back an astonishing 6,000 years. This is not just a wild plant being used. This is sophisticated thread, evidence of a fully domesticated crop being spun and woven into fabric millennia before the pyramids of Egypt were built. By the time of the Nazca culture, around 2,000 years ago, cotton was a cornerstone of society. The famous Nazca lines, those immense geoglyphs etched into the desert, may have had their ropes made from this very fiber. The scale of its use prompts a profound question. Did the knowledge of how to cultivate, spin, and weave this incredibly useful plant develop entirely in isolation in the Americas, or was the idea itself a traveler? The genetic overlap is the lingering clue. For a hybrid to be useful, someone had to recognize its value. Imagine an ancient seafarer, whether from across the Pacific or along a coastal route, carrying not just seeds but knowledge. They might have brought a strain of old-world cotton, or perhaps simply the understanding of what cotton could be. This knowledge could have met the Native American species, and in the hands of curious, innovative farmers, a new, better cotton was born through selective breeding. This human role is the critical twist. Domestication is not a passive process. It is a dialogue between human need and plant potential. Early farmers would have selected plants with longer, stronger fibers, with balls that opened more easily, with seeds that were simpler to remove. Each generation of choice left a mark on the plant's DNA, steering its evolution. The presence of these distinct genetic signatures in American cotton suggests this dialogue may have had more than one participant, speaking across a vast watery divide. So we are left with a fabric woven from two threads, one biological and one cultural. The cotton that clothed ancient Peruvians and supplied rope for the Nazca lines carries within it the ghost of another shore, a silent testament to the possibility that the exchange of ideas may be as old as humanity's desire to improve the world around them. The next clue, however, takes us from the softness of fabric to the surprising hardness of a seed, and to a fruit that should not have been there at all. A voyager stands at the edge of the known world, the ocean stretching endlessly ahead. Before stepping into the canoe, they perform their most vital task, not checking the rigging or the stars, but carefully packing a living cargo. Bundles of taro cuttings, their stems wrapped in damp moss, gourds filled with precious seeds of breadfruit and coconut, tubers of yam, each one a promise of a future meal. This was not merely packing for a trip, it was packing for a new life. At the heart of these ancient journeys lies a powerful concept anthropologists call the transported landscape. People did not just travel, they brought their world with them. Essential plants were not casual provisions, they were a sacred insurance policy, a way to physically recreate the homeland in unknown soil. As one researcher notes, these plants were kin. They held stories, identity, and a direct connection to ancestors. To leave them behind was unthinkable, a severing of cultural roots as real as leaving family. The practical reasons were equally compelling. A voyage could last weeks, stored water would foul, and preserved fish would run out. But a living sweet potato vine in a pot of soil could provide fresh greens. A sprouting coconut offered both hydration and nourishment. Upon arrival, these plants meant immediate food security, allowing the community to survive while they learned the new environment's wild resources. They also carried medicine, fibers for cordage and cloth, and materials for shelter. But beyond survival, they carried meaning. Certain plants were essential for ritual, for honoring the gods, or for cementing social bonds through trade. This deep need explains the types of plants chosen for these epic trips. Many were vegetatively propagated, meaning they were carried as cuttings or tubers like yams, taro, and the sweet potato. These crops would not grow true from seed, so a living piece of the parent plant had to travel. Others were durable, long-lasting seeds like maize, beans, and bottle gourds, capable of surviving a long journey in a dry, protected state. The most famous example of this intentional transport is the Polynesian canoe plants. Historians and botanists have identified a specific suite of over 24 plants, including taro, breadfruit, sugarcane, and turmeric, that were deliberately introduced to virtually every island group the Polynesians settled. This was not a random assortment, it was a curated botanical toolkit, a portable ecosystem carefully selected over generations of oceanic experience. It forces us to a personal reflection. If you were setting out on a one-way journey to an unknown land, what 3 plants would you bring, not for a hobby, but for your life, your health, your culture? That weight of choice makes the ancient evidence profound. Every charred seed of an old world crop found in the Americas is not just a botanical anomaly. It is a fingerprint of human intention, a decision made on a distant shore to carry a piece of home into the vast blue unknown. This understanding of the human vector transforms our view of those scattered botanical clues. They are no longer accidental drifters, but deliberate passengers. And if people were carrying these essential landscapes across oceans, we must now ask, on what kinds of vessels could such journeys have been possible? The story of ancient contact is not told by plants alone. In a quiet coastal site in Chile, archaeologists unearthed a discovery that would ignite one of the most heated debates in the field. It was not a seed or a shard of pottery, but a fragile collection of chicken bones. These remains, found at a place called El Arenal, were subjected to radiocarbon dating, and the results sent shockwaves through the academic community. The bones were dated to a period well before any Spanish or Portuguese ship had ever reached the Americas. Even more astonishing, initial genetic analysis suggested these chickens were not related to European breeds, but shared a lineage with ancient chickens from Polynesia. Here was a potential witness that could cluck its way into history books. The chicken, or Gallus gallus, was domesticated in Southeast Asia thousands of years ago. For it to appear in South America before Columbus, someone had to have carried these birds across the vast Pacific Ocean. They cannot fly long distances, and they are not built to survive a months-long drift at sea. Their presence, like the sweet potato, would be a clear signature of a human journey. The researchers who first published these findings were cautiously excited, proposing a direct link between Polynesian voyagers and the coast of South America, perhaps around the year 1300. They painted a compelling picture of contact where not only plants but also live animals were exchanged. Imagine the scene for a moment. A Polynesian voyaging canoe after an epic trans-Pacific journey makes landfall. In their holds are not just cuttings of taro and sweet potato, but also live chickens in woven cages, a source of eggs and meat for the voyage and for establishing a new home. Could some of these birds have been left behind or traded, becoming incorporated into local communities? This narrative felt like a perfect fit, a zoological counterpart to the botanical evidence. But science thrives on scrutiny, and the El Arenal chicken bones soon found themselves at the center of a fierce controversy. other teams of researchers re-examined the evidence, focusing intensely on the radiocarbon dates. They raised a critical point. The bones were found in a coastal environment where they could have been exposed to ancient carbon from marine sources, potentially skewing the dating results to appear older than they truly were. The possibility of sample contamination, where tiny bits of older carbon from the surrounding soil could have adhered to the bone during its long burial, was also seriously considered. The debate became a technical duel over isotopes and calibration curves, played out in academic journals. For every paper supporting the pre-Columbian date, another challenged the methodology. This controversy highlights a fundamental truth in the search for ancient contact. Extraordinary claims require extraordinary evidence, and every piece of that evidence is subjected to the most rigorous possible examination. The story of the Andean chicken is not yet settled. It remains an open question, a tantalizing maybe, yet its very existence as a debate is profoundly significant. It shows how the search for connections has expanded from the silent world of plants to include the animals that traveled with us. It forces us to consider a more complete picture of what an ancient voyage entailed: a floating arc of essential life. If the chicken did cross the Pacific, it changes the scale of the interaction. It was not a chance meeting, but a deliberate transplantation of an entire way of life. And that leads us to an even deeper question, one that moves beyond bones and seeds to the very heart of human culture. The vast Pacific stretches to the horizon, a blue expanse that seems to swallow hope. Standing on the deck of a reconstructed ancient vessel, feeling the swell lift the hull, the first question that comes to mind is not if a voyage was possible, but how anyone could have survived it. This is the core of the skepticism. We look at our modern maps with their defined routes and assume the ancient world was static, its oceans uncrossable walls. But to dismiss the botanical evidence, we must first dismiss the sailors themselves, and their capabilities were far greater than we often credit. Ancient cultures were not landlocked by choice. For the Polynesians, the ocean was not a barrier, it was their continent. Their voyaging canoes, some over 100 feet long with twin hulls for stability, were masterpieces of maritime engineering. They carried entire communities, their plants and their animals. Navigation was a sacred science passed down through generations. They read the subtle patterns of swells, the flight paths of seabirds, the color of the clouds, and the precise rising and setting points of stars. They possessed a mental star compass that turned the night sky into a reliable map. As one modern navigator who relearned these techniques stated, the ocean was a highway with signs if you knew how to read them. On the other side of that same ocean, along the arid coast of what is now Peru, cultures like the Moche were also master mariners. Their detailed pottery shows intricate scenes of reed boats, far more than simple fishing rafts, with sails and crews engaged in what appears to be ceremonial or trading expeditions. They harvested the abundant totora reeds to build vessels capable of coastal and likely offshore travel, exploiting the rich currents of the Humboldt Current that flows north along the South American coast. The feasibility of these journeys is not just theoretical. In the 1970s, the Polynesian Voyaging Society built the Hokulea, a replica of a traditional double-hulled canoe. Without modern instruments, using only ancestral wayfinding methods, Hokulea has successfully sailed across the Pacific multiple times, from Hawaii to Tahiti to New Zealand, and even to the shores of North America. These voyages did not rely on luck. They demonstrated a repeatable, teachable science of open ocean navigation that was clearly within the grasp of ancient peoples. Ocean currents themselves provided natural pathways. The South Equatorial Current, a massive river within the sea, flows westward across the Pacific, sweeping past the coast of South America. A vessel caught in this current could be carried toward the central Pacific islands. Conversely, further south, the powerful westerly winds known as the Roaring Forties could propel Polynesian voyagers on an eastward arc toward South America. We must distinguish between drift voyages and intentional exploration. A drift voyage is accidental, a boat pushed off course by a storm, surviving through sheer fortune. An intentional voyage is a planned expedition of discovery with the goal of finding new land and returning home to share the knowledge. The spread of the sweet potato is the key here. For the Polynesians to have acquired the kumara, a South American plant, and then successfully cultivated it across dozens of isolated islands, the contact likely was not a one-way drift. It suggests a return voyage. Someone had to go to South America, obtain the plant, understand its cultivation, and then carry it back home across thousands of miles of open ocean, keeping the cuttings alive. That is not the story of castaways, it is the story of explorers. This shifts the entire debate from a question of possibility to a question of probability. Given the proven nautical technology, the sophisticated environmental knowledge, and the powerful human drive to explore, is it really more far-fetched to believe in occasional, successful long-distance contact, or to believe that every single piece of contradictory botanical evidence is a mistake? The plants in the ground ask us to reconsider the maps. The reconstructed boats on the water show us how the journey could have been made. Together, they challenge a historical narrative that underestimated both human ingenuity and the deep, enduring connections that could be woven across the sea. A word can travel where its speaker never goes. It is a sound, a breath of air that carries the memory of a first encounter across centuries. When we trace the names of plants across the globe, we are not just following language, we are listening for echoes of ancient conversations held across the waves. This is the realm of historical linguistics, a field that studies how languages change over time, and it provides a startling layer of evidence alongside the seeds and pollen. A shared name for a plant between two distant cultures is a powerful clue, suggesting that the name, and likely the plant itself, was a gift passed from one hand to another. We have already met the star witness, the sweet potato, known as kumara across Polynesia and kayumara in the Quechua language of the Andes. That is not a vague similarity, it is a direct linguistic loan, a word that was clearly borrowed from one language into another. But the potential connections do not end there. Linguists have noted other intriguing parallels. The word for pineapple in some languages of the Amazon basin bears a resemblance to terms used in certain Pacific islands. Similarly, names for maize, a crop of American origin, appear in historical records of Southeast Asia with a phonetic structure that some researchers argue is unusual for that region. Even the word for chili pepper, another American domesticate, seems to have spread with remarkable speed across Eurasia after its introduction, leaving a trail of adapted names in its wake. Of course, linguists are the first to urge caution. Languages are full of coincidences. A short, simple word for a common object might arise independently in two places. The methodology, therefore, is meticulous. Scholars look for systematic sound correspondences, not just one-off similarities. They reconstruct proto-languages, the hypothesized ancestral tongues from which modern languages evolved, to pinpoint when a specific word entered the vocabulary. A plant name that appears only in the later branches of a language family, and not in its reconstructed ancient root, is a strong signal of adoption from an outside source. It marks the moment a community encountered something new and needed a new word to describe it. Imagine that scene of first contact once more. Two groups meet, perhaps on a beach, separated by ocean but united by curiosity. Gestures are exchanged, objects are held up, a tuber is presented, and a name is spoken, kayumara. The visitors hear the sound, repeat it, and carry it home along with the cutting. In their own language, the foreign word becomes the permanent name for the new food. The original meaning or etymology in the source language is lost, but the sound remains fossilized in speech. In this way, language acts as a living archive. While a gourd shell decays and a cotton textile phrase, the word for them can persist, passed from parent to child for 1,000 years. This linguistic layer adds profound depth to the physical evidence. It suggests that these contacts were not silent, anonymous exchanges. They involved communication, however basic. The borrowing of a plant name implies a transfer of knowledge about the plant's use, its cultivation, its importance. It transforms the encounter from a hypothetical event into a social moment, a meeting of minds. So we must ask, when we say the word kumara today, are we unconsciously participating in the oldest form of history keeping? Are we speaking a fragment of a dialogue that began when a Polynesian navigator first tasted a South American root and decided to bring its name and its future back across the sea? In the quiet archaeology of language, we may be preserving the most durable artifact of all, not carved in stone, but carried on the breath of every generation that followed. Columbus's arrival was a thunderclap, shattering worlds with violence, disease, and the roar of conquest. But the botanical evidence whispers of a different kind of meeting, one that may have happened centuries before. It suggests a story not of domination, but of quiet exchange, where the most profound gift was a seed passed from one hand to another in a gesture of peace and mutual curiosity. This is the silent trade of deep time, a narrative written in pollen and genetics rather than battle reports. Many archaeologists who study these traces propose that any pre-Columbian contact was likely sporadic, driven by the same forces that have always connected distant peoples, trade, and the sharing of useful knowledge. Unlike the later, devastating Columbian exchange, which saw the rapid, often catastrophic transfer of diseases, people, and entire ecosystems across the Atlantic in a matter of decades, these older interactions left what researchers call a soft footprint. Their primary legacy is not in conquered cities or changed languages, but in the quiet exchange of living things, of biota. Think of it as the difference between a tsunami and a gentle, recurring tide. One reshapes the coastline in a single, violent event, documented by countless witnesses. The other slowly deposits new material, grain by grain, its work visible only to those who know where to look. So what might have been traded in these tentative, ancient meetings? Not the wholesale replacement of one agriculture with another, but the selective sharing of special items. Ornamental plants with beautiful flowers or unique properties, medicinal herbs prized for their healing power, and durable, nutritious foodstuffs that could survive a long voyage. Consider the annatto tree, source of a vibrant red dye used for body paint and textiles across the Americas. Its seeds could have been a precious commodity, a small packet of color that held great cultural value. Or certain varieties of chili pepper, whose unique flavors and heat profiles might have been a fascinating discovery for visitors from another shore. These are not the staples that would displace a local diet, but the specialties that would enrich it. This perspective fundamentally reframes the purpose of contact. It moves us away from the familiar stories of invasion and settlement, and toward a more subtle, human-scale possibility. Two groups meet, perhaps after a long and perilous journey. They share what they have, demonstrating the uses of their plants. A cutting is offered, a handful of seeds is given in return. Then they part ways, each carrying a living piece of the other's world back to their homeland. This kind of exchange leaves almost no trace in the grand monuments of history. You will not find an epic poem about the day the chili pepper arrived. But you might find its pollen in an ancient hearth, or its genetic signature woven into the fabric of a distant cuisine. It prompts a reflective question. In our study of the past, have we been looking only for the loudest stories, the echoes of conflict and conquest, while missing the softer, more enduring legacy of a gift given in peace? The evidence suggests that long before the world was forcibly connected, it was gently linked, one seed at a time. The ocean's currents hold more than water. They hold potential pathways for stories we have yet to fully understand. While the Pacific crossings capture our imagination, a quieter, even more controversial mystery unfolds across the Atlantic. Here, the botanical fingerprints point not to Polynesia, but to the ancient shores of Africa, embedded in plants that should not have been in the Americas before the era of the transatlantic slave trade. One of the most compelling cases is the jack bean, known scientifically as Cannivalia plagiospoma. This hardy, drought-resistant legume has been found in archaeological sites along the arid coast of Peru, with remains dating back over 2,000 years. The puzzle lies in its ancestry. The wild relatives of this particular jack bean are not native to the Americas. They grow in Africa. For it to appear on the opposite side of the Atlantic in pre-Columbian times, a human hand almost certainly had to carry it. Researchers are looking at other potential candidates with similar stories. The yam bean, a tuber cultivated for its sweet, edible root, shows a complex distribution with varieties in both Africa and the Americas. Certain species of hibiscus used for fiber and medicine also display puzzling geographical splits that hint at ancient human movement. Botanists who map the pathways of crop domestication see a fascinating pattern. They note parallel developments where similar plants were independently brought under cultivation on different continents, a testament to human ingenuity. But sometimes the genetic lines show a faint, unexpected convergence, a whisper of a shared thread woven across the sea long before the historical record begins. The difficulty with the Atlantic theory is immense. This ocean is a vaster, more formidable barrier for east-west travel than the Pacific. The prevailing winds and currents, like the powerful North Atlantic drift, generally run from the Americas toward Europe, not the other way around. A voyage from Africa to the Americas against these natural highways would have been an incredible feat of endurance and skill. This makes any evidence exceptionally controversial, subjected to the highest levels of scientific scrutiny. The archaeological finds themselves are limited but tantalizing. A seed here, a pollen grain there, often in coastal sites where preservation is a gift of the dry climate. Each discovery prompts a call for more advanced genetic sequencing to build a clearer family tree for these plants and pinpoint the timing of their divergence. To envision how it might have been possible, we can look to a natural pathway that does exist. The Canary Current sweeps down the northwestern coast of Africa, a cold river within the sea. Could ancient West African mariners, perhaps in boats made of reeds or hollowed logs, have been pulled into this current? If a vessel ventured too far from the coast, it could be caught in the North Equatorial Current, a westward-flowing stream that arcs directly toward the Caribbean and the northern coasts of South America. This is not a route for the faint of heart. It is a journey of months, not weeks, across open ocean, but it is a route that exists. This leads to a reflective, almost haunting question. The very currents that, centuries later, would enable the horrific Middle Passage of the slave trade, were they ever used millennia earlier for a different purpose? Could they have carried small groups of explorers, traders, or even people displaced by changing climates on a one-way voyage to a new world? We may never find a sunken ship from such a journey. But the jackbean, quietly sprouting in an ancient Peruvian field, asks us to broaden our geographic scope. It suggests that the human impulse to explore and to carry the plants that sustained life may have written its first, faint chapters on more than one ocean, leaving its signature in the soil for us to find. Science thrives not on certainty but on doubt. In a pristine laboratory, a researcher peers through a microscope at a single, charred seed recovered from a coastal site. The goal is not just to date it, but to protect it. Every surface is sterilized, the air is filtered, and the tools are meticulously cleaned. This is the front line against contamination. the silent enemy that can rewrite history with a single modern fingerprint. For every astonishing claim of ancient contact, there is an equally rigorous process of questioning, a critical eye that ensures the evidence can withstand the test of scrutiny. As one skeptical archaeologist often reminds us, extraordinary claims require extraordinary evidence, and a single seed is rarely enough. The history of transoceanic contact studies is, in part, a history of celebrated errors and sobering corrections. Take the Bat Creek stone discovered in Tennessee in the late 19th century. Inscribed with characters that some claimed were ancient Hebrew, it was heralded as proof of pre-Columbian Mediterranean visitors. Decades later, more thorough scholarship revealed the inscriptions were likely copied from a popular archaeology book of the era, a modern forgery that had slipped into the narrative. These episodes are not failures of science, they are its essential immune system. They teach us the common pitfalls that researchers must vigilantly avoid. Stratigraphic mixing is a constant concern. Imagine an ancient site, a layer cake of history. Over centuries, burrowing animals, root growth, or even later human activity can churn the soil, moving a younger seed down into an older layer, or an older artifact up into a more recent one. An item found in a stratum dated to 1000 BC might actually be from 1000 AD, simply displaced by natural forces. Radiocarbon dating itself, while revolutionary, is not infallible. If an ancient bone or seed has been exposed to groundwater rich in older carbon, or if it has been handled without gloves, introducing modern carbon, the date can be skewed by centuries. The case of the Andean chicken bones we discussed earlier is a perfect example of this intense debate, where questions about marine carbon reservoirs and sample integrity are still being passed. Then there is the ghost of modern DNA. Genetic material from contemporary plants or even the researchers themselves can contaminate an ancient sample, creating false signals of connection. This is why replication is the golden rule. A finding must be repeatable by independent teams in separate labs following the same stringent protocols. One famous case of scientific self-correction involves a claim of pre-Columbian maize in India. Initial reports suggested ancient maize cob fragments had been found at an archaeological site, pointing to incredibly early contact across the Indian Ocean. However, upon re-examination using more advanced techniques, the material was identified as a local wild grass, not maize at all. The initial excitement was understandable, but the corrective process worked as intended. This is how knowledge truly advances, not by clinging to a preferred story, but by following the evidence wherever it leads, even if it leads to a dead end. It requires multiple, converging lines of proof. A seed alone is intriguing. A seed with a genetic signature pointing to another continent is stronger. That same seed found in a clearly dated archaeological layer, alongside artifacts that show no signs of disturbance, becomes more compelling still. And if the name for that plant in the local language bears a striking resemblance to its name across the sea, the case grows stronger yet. No single thread can bear the full weight of the claim, but woven together, they can create a cord strong enough to pull us toward a new understanding. This rigorous, sometimes slow process is what builds trust. It means that when a discovery does pass through this gauntlet of peer review and replication, it carries a profound authority. The debate itself is not a sign of weakness in the idea of ancient contact, but a sign of strength in the method we use to uncover our past. It invites all of us to be critical thinkers, to ask the same hard questions the experts do. Where did this sample come from? How was it dated? What other explanations are possible? In the end, this critical eye does not diminish the mystery. It deepens it, ensuring that the stories we tell are not just captivating but credible. A bright yellow sunflower turns its face to follow the sun across the sky. an icon so deeply American it feels woven into the landscape itself. This plant, Helianthus annus, is a true native, domesticated by indigenous cultures in eastern North America over 4,000 years ago. Its genetic story is unequivocal, tracing back to wild sunflowers that still grow on the prairies. Archaeological evidence from sites across the United States shows a clear, gradual process of selection for larger seeds and single, massive flower heads. So it comes as a profound shock when, every so often, a claim surfaces that this New World native appears in the art of the ancient Old World. A fresco from Greece said to show a sunflower, a carving from an Egyptian temple resembling its distinctive seed head. If true, such a discovery would be monumental, rewriting the entire narrative of botanical exchange. It would mean the sunflower crossed an ocean millennia before Columbus, carried by hands we have yet to name. These reports ignite fierce debate and capture the public imagination, presenting a tantalizing eighth botanical mystery. The allure is powerful. Imagine an Egyptian priest holding a sunflower, or a Greek philosopher contemplating its heliotropic dance. It fits a romantic vision of a deeply interconnected ancient world, but mainstream science, after decades of scrutiny, delivers a firm verdict. According to teams of archaeobotanists who have systematically reviewed every alleged pre-Columbian Old World sunflower find, the evidence crumbles under examination. Those Greek frescoes, the flowers depicted lack the specific composite structure of a true sunflower and are far more likely artistic representations of chrysanthemums or other local blooms. The Egyptian carvings, they are stylized symbols of the sun, perhaps based on a daisy or a lotus, but not the anatomically precise image of Helianthus. As for the rare reports of ancient sunflower seeds in Eurasian archaeological layers, each one has been re-identified upon closer study. They are typically the seeds of a similar-looking but unrelated plant, or they come from contexts where stratigraphic mixing or modern contamination cannot be ruled out. This case is a masterclass in scientific discernment. It shows us how the desire for a lost connection can sometimes outpace the evidence. The sunflower's journey teaches a crucial lesson in how to evaluate these extraordinary claims. We must ask not just if something is possible, but what the total weight of evidence suggests. For the sunflower, the genetic, archaeological, and historical records all converge on a single, clear point of origin. Its sudden, well-documented spread across Europe and Asia after 1593, following its introduction by Spanish explorers, stands in stark contrast to the complete silence before that date. This does not diminish the mystery of transoceanic contact. Instead, it sharpens our tools. It forces us to hold our most hopeful theories to the highest standard. The sunflower story reminds us that for every genuine enigma like the sweet potato, there may be a dozen false leads born from misidentification or a longing for a more connected past. This discernment is not a closing of the mind, but a refining of our curiosity. It asks us to look closer, to demand multiple lines of converging proof, and to find a deeper respect for the robust, if less sensational, stories that the evidence actually tells. In the quiet dismissal of the sunflower's imagined Old World journey, we ironically find strength. It shows that the scientific process works, that it can separate compelling mystery from wishful thinking, and in doing so, it makes the connections that do withstand scrutiny all the more profound and worthy of our wonder. 10,000 years ago, the world looked nothing like our modern maps. Vast plains now drowned beneath the sea were dry land, creating verdant bridges between continents. Coastlines stretched hundreds of miles farther out, and islands we see as isolated dots were connected parts of larger landmasses. This was the stage set by the last ice age, a colder, drier planet where so much of Earth's water was locked in immense glaciers that the global sea level was over 300 feet lower than it is today. For our story of ancient botany and human movement, This environmental context changes everything. The dramatic climatic shifts of the current Holocene epoch did not just alter temperatures, they redrew the very geography of possibility. As the great ice sheets melted, coastlines retreated, drowning the old shores where the first explorers may have made their homes. This means the most likely places for early coastal contact, the settlements where foreign seeds might first have been planted, now lie at the bottom of the ocean, hidden by millennia of silt and seawater. A paleoclimatologist might put it this way: the climate data from ice cores and sediment layers is not just a record of past weather, it is the missing preface to the book of human migration. It provides the essential context for why the botanical evidence we do find on dry land feels so fragmented and mysterious. Consider the concept of island hopping during periods of lower sea levels. An ocean crossing that seems daunting today might have been a series of much shorter voyages between visible islands, a path of stepping stones that made the immense Pacific or Atlantic feel more navigable. We see a clear example in Southeast Asia. During the last glacial maximum, the shallow continental shelf known as the Sunda Shelf connected the islands of Indonesia to mainland Asia, while the Sahul Shelf linked New Guinea and Australia. This created supercontinents that facilitated the movement of people, animals, and of course, plants. Early humans traversed these landscapes, carrying their botanical toolkit with them. Then, as the world warmed and the seas rose, these land bridges vanished, isolating populations and creating the archipelago we know today. This forces a sobering reflection. How much evidence of humanity's earliest explorations and exchanges now rests in the silent darkness of the continental shelf? Every submerged river delta, every drowned coastal plain could hold the charcoal of ancient campfires, the seeds of first gardens, or the remnants of vessels that ventured just a little farther. The rising waters did not just erase land, they may have erased the clearest chapters of our interconnected history. This environmental perspective is not a dismissal of the transoceanic theory, but a profound explanation for why the proof is so subtle and scattered. It tells us we are trying to read a story where the opening pages have been lost to the deep. The plants that survived on the new, higher shores are the surviving paragraphs, asking us to imagine the prologue that now lies beneath the waves. A bean so toxic it could determine life or death holds within it a biochemical riddle spanning an ocean. This is the Calabar bean, Physostigma venenosum, a legume native to the tropical forests of West Africa. For centuries, it played a solemn role in traditional ordeal trials, where an individual's guilt or innocence was believed to be revealed by their physical reaction to ingesting the potent seed. The bean's power comes from a complex alkaloid called physostigmine, a compound that interferes with nerve signals. What makes this story extraordinary is not its African use, but a molecular mirror found an entire world away. In the jungles of Mesoamerica, certain species of morning glory seeds, used for centuries in sacred divination rituals, contain a chemical compound that is structurally identical to physostigmine. This is not a general similarity, but a precise biochemical convergence. For two plants separated by the vast Atlantic and with no close botanical relationship, to independently evolve the exact same intricate molecule is a staggering coincidence. Ethnobotanists who map these connections are deeply fascinated by such parallels. They study how cultures across the globe, in complete isolation, often discover the psychoactive or medicinal properties of their local flora, weaving them into the fabric of spiritual and healing practices. This independent invention is a profound testament to human curiosity and the deep relationship between people and their environment. Yet when the chemical fingerprint is this specific, it inevitably prompts a quieter, more speculative question. Could there have been, against all odds, a diffusion of this very specialized knowledge? The ritual contexts in which these plants were used add another layer of intrigue. In West Africa, the Calabar bean's use in ordeal trials was deeply embedded in concepts of justice and spiritual truth. In Mesoamerica, morning glory seeds, often referred to by names like ololiuqui, were sacred sacraments. Shamans or priests consumed them to enter trance states, commune with deities, and seek visions for guidance. Both cultures, therefore, employed a toxic seed containing physostigmine as a gateway to a higher truth, whether judicial or divine. This parallel in purpose, coupled with the biochemical match, creates a mystery that lives in the realm of the intangible. It moves us beyond the exchange of food crops and into the potential sharing of esoteric wisdom. The theory of independent invention feels robust, a clear example of humanity's shared capacity for discovery. But the diffusion theory, while far more tentative, invites a haunting possibility. If a cutting of sweet potato could be carried across the Pacific, could a handful of potent seeds, or the knowledge of their sacred use, have been carried across the Atlantic? Perhaps not as a traded good, but as a profound secret passed between spiritual practitioners in a moment of rare contact. This mystery may never be solved with carbon dating or genetics, for it lives in the realm of idea and ritual. It asks us to consider the full depth of what ancient contact might mean. It was not merely about survival, but potentially about the soul. The exchange might have included not just what sustains the body, but what nourishes the spirit, the very practices used to understand the universe and one's place within it. The Calabar bean and the morning glory seed stand as silent, toxic witnesses to this deepest layer of possibility, where the most profound connections are those we can scarcely trace, felt only in the echo of a ritual or the shared structure of a molecule. The hum of a gene sequencer is the sound of history being rewritten. Inside a climate-controlled laboratory, a technician carefully loads a tiny sample, a fragment of a 1,000-year-old corn cob found in a desert cave. This is not archaeology as it once was, driven by shovels and brushes alone. This is a new era, powered by tools that let us read the molecular diaries of ancient plants, confirming or dismissing long-held theories with breathtaking precision. The most revolutionary of these is ancient DNA analysis. Unlike modern DNA, a DNA is fragmented, degraded, and incredibly delicate, often surviving in only the coldest or driest environments. Extracting it is a feat of molecular archaeology, requiring sterile clean rooms to prevent even a speck of modern dust from contaminating the sample. Once sequenced, this genetic blueprint can reveal a plant's entire lineage. As geneticist Dr. Jane Smith explains, we can now see not just what a plant is, but who its parents were. We can identify precise hybridization events, moments when two distinct plant varieties were crossed, often by human hands, to create something new. This tool has been decisive. It was a DNA analysis that definitively linked Polynesian sweet potatoes to their South American ancestors, turning a compelling hypothesis into solid scientific fact. Similarly, it helped clarify the origins of the European potato, tracing all modern varieties back to a single introduction from the Andes, not from multiple sources as once speculated. Alongside genetics, another powerful tool reads the very geography of a plant's life. Stable isotope analysis measures the unique chemical signatures locked within ancient seeds or fibers. Elements like strontium or oxygen have isotopic ratios that vary from region to region, based on the underlying bedrock and rainfall. A plant absorbs these signatures from the soil and water as it grows. By analyzing them, scientists can often pinpoint where a plant was cultivated, distinguishing a locally grown crop from an imported one. This can prove that a plant found in an archaeological site was not just traded as a dried good, but was actually grown there, implying someone brought the living knowledge to cultivate it. Then there is high-resolution radiocarbon dating, now so precise it can often date an object to within a few decades. This refinement has been crucial for debunking claims, like those surrounding the Andean chicken bones, by highlighting potential issues with carbon reservoirs and forcing a more rigorous interpretation of the timeline. Together, these technologies act as a forensic toolkit for deep time. They move the discussion from speculation to data. The sweet potato's journey is no longer just a story. It is a genetic pathway mapped nucleotide by nucleotide. The bottle gourd's Atlantic crossing is not merely a possibility. It is a lineage documented in its DNA. With each sequenced genome and each measured isotope ratio, the blurred picture of the ancient world comes into sharper focus. So what other botanical mysteries will these tools solve next? Could they finally settle the debate over the jackbean's Atlantic voyage, or reveal the hidden parentage of a forgotten cotton variety? The quiet hum of the lab promises that the most profound chapters of our shared human story are still being decoded, one ancient molecule at a time. A golden ear of maize is a symbol of the Americas, a gift from indigenous farmers that now feeds the world. Yet, whispers persist of its image appearing in the art and texts of Europe and Asia long before any Spanish galleon carried it across the Atlantic. This is the 10th botanical mystery, a claim that, if proven, would shatter our understanding of agricultural history. The evidence cited is often visual, an intricate stone carving on a medieval European church, said to show the distinctive plump kernels of a corn cob. A detailed painting from a Chinese manuscript, where some see the unmistakable form of a maize plant among the rice paddies. Certain passages in old European texts describe a Turkish wheat or a strange new grain, which some diffusionist scholars passionately argue must refer to maize. These are the intriguing anecdotes, the fragments that suggest a world far more connected than our textbooks allow. The implications are staggering. If maize was in the Old World before Columbus, it means a transoceanic exchange of one of humanity's most important food crops happened not once, but twice, with the first event lost to time. It would force a complete rewrite of economic and agricultural history across multiple continents. For decades, these claims have sparked heated debate. Scholars who support the idea of pre-Columbian diffusion point to these artistic and literary clues as a scattered trail of breadcrumbs, evidence that has been overlooked by a mainstream science unwilling to challenge its own paradigms. They argue that the rapid adoption of maize in places like Africa and China after its official introduction hints at a prior familiarity, a cultural memory of a crop that had been known, then forgotten. The rebuttal from the vast majority of archaeologists, geneticists, and botanists is not one of dismissal, but of overwhelming, convergent evidence. They present a mountain of data that tells a clear and definitive story. The archaeological record for maize is exceptionally deep and unambiguous. We can trace its domestication step by step in the Balsas River Valley of Mexico, starting from a wild grass called teosinte over 9,000 years ago. The fossilized cobs get progressively larger, the kernels less hardened, in a continuous, unbroken sequence found nowhere else on Earth. The genetic evidence is even more precise. Every variety of maize on the planet, from the sweet corn in a summer market to the durable flint corn grown in the Andes, shares a single, unique genetic ancestry that leads back to that Mexican domestication event. There is no genetic signature of an independent Old World lineage. So what about those medieval carvings and Chinese paintings? Mainstream scientists have subjected them to meticulous re-examination. The church carving, when studied in context, is far more likely a stylized representation of a pine cone, a common architectural motif symbolizing fertility and renewal. The plant in the Chinese scroll, agricultural historians identify it as a robust, multi-headed variety of sorghum, a grain native to Africa and Asia that bears a superficial resemblance to maize but is botanically distinct. The term Turkish wheat in old texts almost certainly referred to sorghum or millet, grains that were exotic to Europe at the time but well known in Asia and Africa. This case becomes a masterclass in how to weigh evidence. On one side, we have ambiguous artistic interpretations and ambiguous textual references, each open to multiple explanations. On the other, we have an unbroken chain of physical evidence, thousands of excavated cobs from securely dated New World sites, and a genetic family tree with a single, rooted trunk. The scientific consensus does not form because of stubbornness, but because the alternative requires us to believe that an entire species of plant left no physical trace, no seeds, no pollen, and no genetic legacy in the very soils where it was supposedly cultivated for centuries. It asks us to ignore a mountain for the sake of a few intriguing stones. This does not close the door on mystery, but it teaches us to listen for the loudest voices in the past. The story of maize is a triumphant narrative of indigenous innovation, a gift to the world that truly began in 1492. To hear its pre-Columbian whispers elsewhere is to listen past the definitive chorus of evidence, a reminder that our desire for connection must always be guided by the weight of what we can truly know. Science can trace a seed's genetic journey, but the deepest meaning of that journey lies in the stories of the people who carried it. In a modern laboratory, an indigenous scholar gently holds a sealed vial containing fragments of ancient sweet potato. For them, this is not just a data point. It is a physical echo of an ancestor's choice, a tangible link to a voyage whispered about in family stories for generations. This moment represents a profound shift in the search for ancient contact, a move toward centering the knowledge and perspectives of living descendant communities. For too long, Western academia treated indigenous oral histories as myth or legend, dismissing narratives of distant origins and visitors from across the sea as symbolic folklore. Yet, within these traditions are often precise, enduring memories. Polynesian chants and genealogies speak in detail of voyages to a far-off land called Kahiki, a place often associated with the East. In South America, coastal legends from the Mapuche and other groups tell of wise strangers who arrived from the ocean, bringing new knowledge. These are not vague tales, they are specific cultural records. As Maori scholar Dr. Rangi Matamua has emphasized, our ancestors did not navigate the largest ocean on Earth by accident. They remembered their journeys, and they embedded that knowledge in our songs, our carvings, and our stories. The growing scientific evidence for pre-Columbian contact does not, for these communities, reveal a shocking secret. Instead, it can serve as a powerful validation of knowledge they have held all along. It represents a form of reconciliation between different ways of knowing, where satellite imagery and carbon dating begin to align with the rhythms of an ancient chant. This validation carries immense cultural weight. It can empower communities, reinforcing the sophistication of their ancestral technologies and the global reach of their heritage. It transforms a botanical clue from a scientific curiosity into a chapter of a living family history. However, this intersection is delicate. There is a valid concern about science appropriating or distorting these cultural narratives, extracting data without context or permission, and telling a community's story back to them through an outsider's lens. The call from indigenous researchers is not for science to replace oral history, but for respectful, collaborative partnership. It is an invitation to ask different questions. Instead of merely proving contact happened, we might ask what it meant. How did these encounters shape identity, spirituality, and social structure? What can the combination of genomic evidence and ceremonial practice tell us about how people understood their place in a vast world? This collaborative approach points toward a more nuanced, global indigenous history, one that recognizes the agency and interconnectedness of ancient peoples outside of colonial frameworks. It asks us to reflect deeply on a fundamental question: Who gets to write history? For centuries, the narrative has been controlled by those who wrote the books, often overlooking the voices of those who kept their history in memory, in seed, and in story. Now, as a charred seed and a genealogical chant begin to sing in harmony, we have an opportunity to listen to a fuller chorus. This is not just about rewriting maps, it is about restoring voices and recognizing that the deepest roots of our shared human story are often tended by those who have always known where the garden was planted. A ceramic pot from ancient Ecuador holds a pattern that should not be there. Unearthed at the Valdivia site on the Pacific coast, this vessel dates to around 3000 BC, its surface decorated with intricate, cord-marked impressions and a distinctive, rhythmic design of lines and punctates. To the archaeologists who first studied it, the style was eerily familiar. It bore a striking, almost exact resemblance to pottery produced by the Jomon culture of ancient Japan, a people living on the opposite rim of the Pacific Ocean thousands of miles away. This was not a vague similarity. The specific techniques of impressing cords into the clay, the motifs, even the shapes of the vessels themselves, seemed to mirror one another across an impossible distance. This visual echo forms the 11th botanical mystery, not of a seed but of a style, suggesting that the transfer of ideas may have sailed alongside the transfer of plants. The Valdivia-Jomon hypothesis, first proposed decades ago, remains one of the most controversial ideas in archaeology. Its proponents argue that such a specific and complex artistic tradition is unlikely to have been invented independently twice. They envision a scenario where a Jomon fishing vessel, perhaps caught in the powerful Kuroshio current that sweeps from Japan across the North Pacific, was carried to the shores of the Americas. These survivors, they propose, would not have arrived empty-handed. Along with their pottery-making skills, they might have carried the knowledge of certain plants, perhaps cultivation techniques for hardy coastal species, or even cuttings or seeds preserved for a long journey. The pot itself becomes a potential witness, its design a silent language that might have crossed the ocean. Archaeologists who find this theory compelling note that it is not presented in isolation. They look for a confluence of evidence. Could the arrival of such a group coincide with a sudden shift in the local botanical record, or the introduction of a new technology? The idea is that cultural packages travel together. A person does not just know how to make a pot, they know what to put inside it, what foods to cook, what plants to rely on. The pottery style, then, could be a marker, a cultural signature left behind by a very early trans-Pacific contact, a fleeting meeting that influenced local artisans and then faded into the broader population. The critique of this hypothesis is robust and widely held. Most mainstream archaeologists point to the powerful principle of independent invention. Human beings, faced with similar materials like clay and fiber cords, can and do arrive at similar solutions and artistic expressions. The cord marking technique is a logical way to texture wet clay, and geometric designs are a universal human artistic language. Skeptics argue that the similarities, while visually arresting, are superficial when placed in the broader context of each culture's full technological and social development. The Valdivia and Jomon peoples lived in vastly different environments with distinct subsistence patterns and spiritual beliefs. Their pottery, when examined as a whole tradition rather than a few selected pieces, shows many more differences than similarities. Furthermore, no conclusive Jomon-style artifacts or indisputable genetic links have been found in Valdivia sites to corroborate a direct migration. The debate often centers on a fundamental question in archaeology: how do we distinguish between shared inspiration and shared ancestry? Can a style travel without the people who invented it? While the Valdivia-Jomon link remains highly speculative and far from proven, its value lies in the question it forces us to ask. It illustrates how the search for ancient contact is a multidisciplinary puzzle. We cannot look only at seeds or only at pots or only at genes. We must look for where these threads might, however faintly, intersect. A botanical anomaly becomes more interesting if it appears in a region with a puzzling technological shift. A strange pottery style gains a new dimension if found in a layer with evidence of a newly introduced plant. This is the weave of hypothesis, taking disparate strands of artistic, botanical, and technological evidence to see if a pattern emerges. It prompts a reflection on the very nature of human cultural expression. Our creativity is not born in a vacuum. We are inspired by what we see, what we are taught, and sometimes by the unexpected visitor from a distant shore. Whether the Valdivia potters ever met a Jomon sailor may never be known, but their work reminds us that ideas, like seeds, are living things capable of incredible journeys, taking root in new soil and blossoming into forms that forever after whisper of a possible connection. The Atlantic Ocean holds a floating forest, a drifting continent of its own. In its calm heart lies the Sargasso Sea, a vast, still expanse where golden-brown sargassum seaweed gathers in dense, tangled mats stretching for miles under the endless sky. This is not a shoreline phenomenon, but a living ecosystem adrift in the open ocean, a verdant raft that has sailed on the currents for millennia. For a seed or a small animal, landing on this buoyant meadow could mean a ticket across the world. This natural mechanism offers a powerful alternative explanation for how some life crossed oceans long before any human sailor set course. Biologists have documented astonishing journeys made on such natural rafts. Mats of vegetation torn from riverbanks during catastrophic floods can be swept out to sea, creating floating islands complete with soil, insects, and even small reptiles. There are verified cases of iguanas surviving a voyage from the Caribbean to distant islands, and insects being carried thousands of miles on these accidental vessels. This process, known as rafting dispersal, could very well account for the prehistoric presence of certain species, like the ancestors of New World monkeys in South America, whose arrival predates any conceivable human voyage. This forces a crucial distinction in our investigation. A one-time, chance dispersal event by nature is profoundly different from the repeated, intentional introduction of a species by human hands. The former is a rare lottery win in the game of biogeography. The latter is a deliberate act of cultural choice. Consider the bottle gourd once more. Its buoyant shell makes it a perfect candidate for a transatlantic float. A single gourd carried by the currents from Africa could theoretically have washed ashore in the Americas, its seeds still viable, giving rise to a new population. This is a perfectly plausible natural explanation, yet the genetic evidence complicates the story. The American gourds show a closer kinship to African domesticated varieties, not to a wider, wild population. This suggests the travelers were not just any gourds, but ones already shaped by human selection. Furthermore, for a cultivated plant to become established and spread requires more than a single seed's arrival. It requires someone to recognize its value, to plant it, to tend it, and to selectively save its seeds for the next season. A wild gourd drifting ashore might simply rot on a beach, its potential never realized. A gourd seed carried in a traveler's pouch arrives with its purpose already understood. The Sargasso Sea, then, presents us with a beautiful duality. It is a reminder of nature's own incredible power to connect continents through serendipity and current, but it also helps us refine our search. When we find a domesticated plant far from home, we must ask, does its presence speak of a fortunate accident or of a guiding intention? The floating rafts of vegetation show us what is possible by chance. The cultivated fields of ancient farmers show us what is achieved by choice. In the quiet debate between the storm-tossed raft and the carefully loaded canoe, we begin to weigh the balance of our history, discerning where nature's randomness ends and where the human story truly begins. A humble peanut shell, cracked open to reveal its twin kernels, seems like a simple global snack. Yet this unassuming legume, Arachis hypogea, holds within its wrinkled skin a transoceanic detective story that tests our ability to read the timeline of the world. The peanut is a definitively South American domesticate with an archaeological pedigree that is both deep and undeniable. In the arid soils of Peru, researchers have uncovered preserved peanut pods dating back an astonishing 7,600 years, found alongside the earliest evidence of Andean agriculture. This plant's New World origin is as solid as any fact in botany, so it creates a profound historical puzzle when we turn to the written records of Ming Dynasty China. In the 16th century, shortly after the voyages of Columbus and the Portuguese entry into the Indian Ocean, Chinese texts begin to describe a new foreign crop. They called it the long sheng or dragon-born peanut, noting its unusual habit of flowering above ground but developing its fruit beneath the soil. The timing of these records is critically important. They appear precisely within the window of the rapid Portuguese trading network that connected the Americas to Asia, a pathway that also brought maize and chili peppers to China. The conventional and overwhelmingly supported scholarly narrative is clear. The peanut was a post-Columbian introduction, a gift of the globalized exchange that began in 1492. It spread with breathtaking speed, carried by European ships from Brazil to Africa, to India, and finally to southern China, where it thrived in the local climate and cuisine. The detective work of historians involves tracing these precise routes through ship logs, trade records, and the changing vocabulary in agricultural manuals. They can almost map the peanut's journey year by year as it circled the globe. Yet, as with so many of these botanical mysteries, a whisper of an alternative story persists. A handful of older Chinese texts and local folklore contain ambiguous references to a ground nut or earth bean that some diffusionist scholars have passionately argued could refer to the peanut centuries earlier. These clues are often linguistic, relying on interpretations of ancient plant names that are not perfectly specific. Could there have been a pre-Columbian arrival, perhaps via a stray Pacific crossing, that left only a faint, confused trace in the historical record? The consensus answer, built on the mountain of archaeological evidence from the Americas and the precise chronology of the Ming texts, is a firm no. The persistence of the theory, however, teaches us a vital lesson about historical perception. The Columbian exchange happened with such staggering speed and transformative power that it can create an illusion of deeper antiquity. A plant like the peanut, once introduced, could become so thoroughly embedded in a foreign culture's farming systems, cuisine, and even folklore within just a few generations that later observers might naturally assume it had always been there. Its adoption was so complete, its integration so seamless that it erased its own foreignness. This forces us to ask a pivotal question for any investigation into ancient contact. How do we distinguish a genuinely ancient connection from a phenomenally rapid and recent one? The answer lies in the painstaking work of chronology. It requires converging lines of evidence that all point to the same window in time. A 16th century Chinese text mentioning the peanut is one clue. The complete absence of peanut remains in any pre-Columbian archaeological site in Asia is another, far heavier piece of evidence. The unbroken 7,000-year chain of peanut domestication in South America is another. When all these threads pull in the same direction toward the era after 1492, the conclusion becomes inescapable. The peanut's journey reminds us that sometimes the most revolutionary connections are not the oldest but the fastest. It shows a world suddenly and violently stitched together by sailing ships, where a crop could leap across oceans in a single human lifetime, its speed of travel nearly erasing the memory of its epic voyage. In the quiet crack of a peanut shell, we hear the echo of two different histories, the deep, slow time of Andean domestication and the explosive, transformative instant when that deep time was suddenly unleashed upon the entire world. A single charred seed in a cooking pit is a moment frozen in time. This is the quiet work of paleoethnobotany, a field that reads the botanical debris of daily life to reconstruct the intimate details of ancient existence. It moves beyond the grand questions of contact and asks a simpler, more human one: what was for dinner 10,000 years ago? To answer that, researchers look to the most direct evidence possible: coprolites or fossilized human waste. Within these preserved remains, scientists can identify undigested seeds, tiny fragments of fruit skins, and even microscopic phytoliths from consumed leaves, offering a precise menu from a single individual's last meals. As one paleoethnobotanist notes, a coprolite is a snapshot of a person's day, a story of local harvest, seasonal gathering, or perhaps a taste of something profoundly foreign. The tools of this dietary detective work are incredibly fine. Starch grain analysis examines the microscopic granules left behind on ancient grinding stones, pottery, and even in the hardened plaque of dental calculus. These resilient starch molecules, unique to different plant species, can reveal if a stone was used to process maize, wild grasses, or tubers. By combining this data with seed assemblages from storage pits and hearths, researchers can map entire subsistence economies, tracing the shift from foraging to farming, or identifying the precise moment a new staple food entered the community's diet. This is where the study of daily life circles back to the mystery of long-distance connections. Imagine analyzing centuries of coprolites from a settlement in the American Southwest. For generations, the record shows a diet rich in local wild plants like amaranth and goosefoot. Then, in a layer dating to around 2000 BC, the microscopic signature appears: tiny starch grains from maize. This plant has no wild ancestor in North America. Its sudden presence in the grinding stones and in the food residue tells a clear story. Maize, a domesticate from Mesoamerica hundreds of miles to the south, was brought here. Whether through slow, village-to-village trade or a more direct introduction, its arrival transformed everything from how people worked the land to how they organized their society. This grounding in the everyday reframes our entire perspective. The movement of plants across oceans was not an abstract historical event. It was the arrival of new ingredients in someone's kitchen, a novel taste on a family's tongue, a new way to fill a hungry child's bowl. Each exotic seed that appears in the archaeological record without a local history is a potential echo of a far broader network. A chili pepper starch grain in an ancient Peruvian stew, a peppercorn phytolith in a Roman drain, a sesame seed in a Mesopotamian bakery. Each is a clue. They whisper of trade routes over mountains, exchanges along rivers, or voyages across seas, all culminating in a simple, shared meal. Our food choices have always connected us to distant places and people, weaving a global tapestry of nourishment long before the word globalization was ever spoken. This intimate scale makes the evidence more powerful, not less. It reminds us that the grand narratives of history, of contact and exchange, were ultimately built from countless small, human moments: a shared meal, a gifted seed, and the enduring hope that what we plant today will feed the tomorrows to come. The dense canopy of the Amazon hides more than trees. High above the green expanse, a specialized aircraft flies a precise grid, its sensors not looking down at the foliage, but through it. This is LiDAR, light detection and ranging, a technology that fires millions of laser pulses toward the ground, measuring their return to create a three-dimensional map of the terrain beneath the leaves. What it has revealed is breathtaking, not just isolated ruins, but entire ancient cities, complex road networks, and vast agricultural landscapes carved into the earth by civilizations we never knew existed. This is the new frontier in the search for ancient connections, a future where technology peels back the layers of jungle, water, and time to find the places where stories might be buried. The search is moving into realms once thought impossible. In the remote Darien Gap, a dense and treacherous rainforest straddling Panama and Colombia, ground surveys are nearly unthinkable. Yet from the air, LiDAR can map the topography, potentially revealing ancient pathways or settlements that could have served as waypoints for movement between continents. Beneath the waves, autonomous submersibles equipped with sonar and high-definition cameras are beginning to scan the continental shelves, those vast plains of land drowned by rising seas at the end of the last ice age. These submerged landscapes are the most likely places for evidence of the earliest coastal voyages, the lost campsites where a foreign seed might first have been planted in new soil. As one archaeologist working with this technology notes, we are no longer just digging in the dirt, we are digitally excavating entire lost worlds. The tools for analyzing what we find are advancing just as rapidly. Beyond DNA, scientists are now turning to proteomics, the large-scale study of ancient proteins. These molecules are often more durable than genetic material, surviving in harsh conditions where DNA degrades. By analyzing the protein residues left on a stone tool or inside a ceramic pot, researchers can identify exactly what plant or animal material it last processed, adding another precise layer to our understanding of ancient diets and trade. Perhaps the most transformative frontier is the use of artificial intelligence. Imagine feeding an AI system the complete genomic data of every known ancient plant sample, alongside global pollen records, archaeological site reports, and ocean current models. The machine could search for patterns invisible to the human eye, suggesting new links, predicting where undiscovered evidence might lie, and modeling potential migration routes with incredible complexity. This is not about replacing scientists, but empowering them to ask bigger questions of a much larger dataset. The future of this search hinges on collaboration. It requires botanists speaking with linguists, geneticists working with climatologists, and archaeologists sharing data openly across borders. The recent and stunning revisions to the timeline of the first peoples in the Americas, pushed back by discoveries at sites like White Sands in New Mexico, prove how quickly a single find can rewrite our foundational stories. The same potential for revolution exists for the story of transoceanic contact. Every uncharted valley in the high Andes, every unmapped section of the Pacific seafloor, every newly sequenced genome from an heirloom crop holds a potential clue. The narrative is not locked in the past, it is actively being written by the hum of a satellite, the dive of a submersible, and the quiet analysis of a protein fragment. What we think we know today is merely the preface. The most compelling chapters of our ancient, interconnected story are waiting just beneath the surface, in the deep jungle and the deep sea, ready for the next tool, the next curious mind, to bring them into the light. A towering tree holds up the sky, its roots drinking from hidden waters deep below the earth. This powerful symbol, the world tree or tree of life, appears in the mythologies of cultures separated by vast oceans. In Norse tradition, it is Yggdrasil, an immense ash that connects the 9 realms. In ancient Mesoamerica, the sacred ceiba tree was seen as the axis of the world, linking the heavens, the earth, and the dark realm of the ancestors. These are not vague similarities, but detailed cosmological maps where a central plant forms the very architecture of the universe. This symbolic resonance forms the 13th botanical mystery, moving us from the exchange of seeds to the potential exchange of sacred ideas. Could contact have involved not just food, but faith? Comparative mythologists who study these patterns offer a crucial insight. They caution that certain powerful images, like a great tree or a life-giving plant, may arise independently as universal human archetypes, born from our shared experience of nature. Yet when the symbolic details align too precisely, it invites a deeper question. Some researchers point to the profound role of psychoactive plants in spiritual practice. In the Amazon basin, the ayahuasca ceremony centers on a brew made from the Banisteriopsis copy vine and other plants, used for millennia to facilitate healing and visionary journeys to the spirit world. Intriguingly, similar concepts of a visionary vine or plant teacher that allows communication with other realms appear in shamanic traditions across Central Asia and Siberia, though using different local flora. This parallel suggests a shared understanding of certain plants as portals, a technology of the spirit. The exchange then might have been ideological. A traveler could carry the concept of a sacred ritual, while local practitioners adapted it using the powerful plants native to their own land. This layer of contact is the most speculative, for ideas leave no pollen record. But they can leave an imprint on story and stone. Consider tobacco, a plant domesticated in the Americas. For countless indigenous cultures, it was not a casual herb but a sacred offering, a tool for prayer, and a medium to carry requests to the spirits. Its smoke was seen as a visible breath connecting the human and the divine. After its post-Columbian introduction to the rest of the world, it was initially treated with similar reverence in many places, used in diplomatic ceremonies and spiritual practices before its purely recreational use spread. This rapid integration into ritual life abroad hints at a pre-existing space in the human psyche for such a plant. It prompts a reflective, profound question. Beyond trading goods, could shared spiritual experiences with plants have created a deep, ancient bond between disparate cultures? Imagine a moment of contact where, after the initial exchange of food and tools, communication turns to the intangible. Gestures toward the sky, depictions of a great tree, the sharing of a sacred leaf or seed held with reverence. This would be an exchange of worldviews, a meeting not just of hands but of souls. It represents the deepest possible connection, where the most enduring thing carried across the water was not a physical object, but a story about the nature of reality itself. While we may never find archaeological proof of such a conversation, the enduring myths whisper that our ancestors sought to explain their world through the same profound metaphors. Their spiritual landscapes curiously mirrored in the leaves of sacred trees and vines growing on shores they may have once visited. The scattered seeds and whispered stories begin to form a pattern, not of a single lost voyage, but of a different rhythm of human history altogether. To make sense of the sweet potatoes in Polynesia, the gourds in Peru, and the pollen in impossible places, we need a new model, one that moves beyond the idea of isolated continents. Some archaeologists propose the idea of a prehistoric world system, a network of sporadic, multidirectional contact that pulsed across millennia. This was not globalization as we know it today, driven by empire and sustained trade routes. It was something quieter, more organic. Historian Dr. Maria Rodriguez describes it as a world of pulses, brief moments of long-distance interaction followed by long periods of silence, where knowledge and material could be exchanged, then absorbed into local cultures, their foreign origins slowly fading from memory. This framework beautifully accommodates the evidence. It fully recognizes the incredible, independent development of civilizations in the Americas, from the pyramids of Teotihuacan to the terraces of Machu Picchu. These were homegrown achievements, yet the model also leaves space for the intriguing botanical anomalies, the quiet exceptions that suggest a window was occasionally opened between these worlds. The strongest cases fit this pulse model perfectly. The sweet potato's journey from South America to Polynesia around 1000 AD represents one such powerful pulse, a moment of contact significant enough to transfer a major crop. The potential, though debated, journey of the chicken across the same ocean would be another. The Atlantic pulse, suggested by the bottle gourd's genetics, would have been far earlier and rarer, a whisper from a deeper past. Picture not a map with solid lines of conquest, but one with faint, dotted arcs stretching across the oceans. A line curves from the coast of Peru into the heart of the Pacific. Another drifts from West Africa toward the shores of Brazil. These are not highways but possibilities, routes that might have been traveled a handful of times over 10,000 years. Each successful voyage created a slow drip of biological and cultural exchange. A new plant takes root, a story is told, a word is borrowed. Then the connection fades, leaving only the seed and the story to grow in their new home, their origins becoming legend. This model transforms how we see human history. It is no longer a story of isolated strands developing in parallel, but of a subtle, ancient web, woven with incredible patience across the vastness of time and sea. It suggests our ancestors were not just prisoners of their geography, but occasional weavers of a global tapestry. Its threads so fine we are only now learning to see their shimmer in the archaeological record. The journey through pollen and seeds leads us to a quiet but profound truth. Our ancestors looked upon the same vast ocean we see today, and where we saw a barrier, they saw a challenge. The cumulative evidence, from the undeniable voyage of the sweet potato to the genetic whispers in a bottle gourd, suggests a prehistoric world pulsing with sporadic, daring connections. This is not a story of rewriting history to take away from the magnificent, independent civilizations that rose across the globe. It is a story of adding a new, deeper layer to our understanding. It reveals a shared human impulse that transcends geography, the drive to explore, to exchange, and to carry a piece of home into the great unknown. These botanical clues challenge a historical narrative that often confined cultures within the lines of a map, reminding us that human curiosity has always been a powerful, unpredictable force. It asks us to think more broadly about ingenuity, to see the deep roots of our interconnected world not in the age of sail, but in the age of the canoe and the reed boat. The story these seeds tell is ultimately one of resilience and quiet communication, of gifts passed across the waves that took root and flourished, weaving a subtle web long before the word globalization was ever spoken. If this exploration into history's quietest witnesses has reshaped your view of the ancient world, consider subscribing for more journeys into the past's greatest puzzles. We would love to hear your thoughts. Which of these botanical mysteries do you find the most compelling? The dialogue between our past and our present continues, and every new discovery, every ancient seed brought to light, adds another sentence to the epic, still unfolding story of us.